Assalamu alaikum everyone, this is me Shoaib, and in this video I will show you how you can draw the phasor diagram or the vector diagram of a transformer. We already know that transformer may be of a single phase or three phase, but for this analysis we always take the single phase transformer or the single phase side. And if I draw a schematic diagram of a transformer, then first of all I have to draw this magnetic core. Okay, this core is made of such a material that it should has the low reluctance path for the magnetic flux. Then I have the primary side, let's say P side, and I have the winding like this, and I have also the secondary side like this, and I have the winding also. Let's say this is S P side and this is S side. And what we do actually for a transformer, we give the voltage, let's say V1 in the input side, and we get the output voltage at the let's say V2. And what actually this transformer does, this transformer actually increases or decreases this V1 at the output side. Let's say it may be V2 greater than V1 or V2 less than V1. That's it. So I have drawn the schematic diagram of a transformer, but if I draw the circuit diagram, then it should be look like this one. It's a primary side winding, and this is the magnetic core, and this is the secondary side winding, let's say. But I have drawn this circuit diagram, but this circuit diagram is only the ideal one. In real life nothing is ideal, we have to take the losses. So when ideal thing meets loss, then it becomes the practical one. So to make this one practical, we have to take the loss parts, and we have some losses in transformer. Like first of all we have to take the copper loss, then a leakage reactance part, then third core loss part. And in the core loss we have two components, one is eddy current loss and one is hysteresis loss. So uh, let's say this is the primary side. Okay, so in the primary side we will give this the voltage in this side, let's say is V1, and we have to take the copper loss component, so we have to make a resistance like this, and we also have to take the leakage reactance component, then we have to make a reactance like this, and the core loss component becomes something like this. We have to take the resistance part. This is actually for the core loss, like eddy current loss or hysteresis loss, and this reactance makes the flux. Okay, this is the magnetizing component. So we can say that this is R1, this is X1, this is let's say R0, this is X0, and we can make the circuit complete like this. Okay, and when this transformer comes in performance, then there will be a current flow through this circuit. Let's say this primary circuit takes I1 current from P1 voltage, and the I1 will be further divided into two components. That is I2 prime and I0, and this I0 will further be divided into two components. That's it, IM and IW. So to say that IW is reason for the core loss component, and IM makes the flux, okay, which flux links in the secondary side. So when IM flows, this winding makes flux. Okay, so for making this flux, this winding generates another voltage which is called induced voltage, which we have to say that E1. This is something like this. Okay, and I2 prime, I have not tell you that what is I2 prime. Actually I will tell you later. Then if I write the KVL equation at the primary side, then the equation should be like this one. V1 is equal to I1 R1 plus J I1 X1 minus E1. So you may be surprised with the sign of this E1. You can say that why E1 is negative. E1 is negative because of its characteristics. What is the characteristics? We know from the Lenz law that when there will be the flux is made for the region of V1, and the induced voltage E1 will oppose this V1. For this opposition characteristics, E1 will be in negative sign. So this is the primary side voltage equation. So I think we should go to the next, to the secondary side, because primary side is already done. So in the next secondary side, we have these losses, but we don't take this core loss component because core loss component is done by the primary side. So we take the core loss component at the secondary side, and it should be R2 and X2. And then we will have the output voltage V2. Then if we connect any load at the output side, there will be a current flow which is I2, and this I2 prime is the image of this I2 in the primary side. Okay, so I2 prime is equal to negative of K I2, and obviously there will be the induced voltage E2, because this flux will cut this coil. So this is the secondary side circuit diagram, and if we write the voltage equation in KVL, then we have to write that E2 is equal to I2 R2 plus J I2 X2 plus V2. Very much simple. So we have done the part of the secondary side. Now it's time to draw the vector diagram. So first of all, we have to take the something which is common in the both of the circuit. So which part is common for the primary and also for the secondary? Obviously this is the flux. Let me take another color. Yeah, this flux is common between these two circuits. So we have to draw the phi one first. The flux first. Let's say the flux are like this, and this flux is generated for this magnetization component IM. So IM and phi will be in the same direction or in the same phase. So we have to write IM in this direction. And then we have this E1 and E2. These things are the induced voltage, and these things came for the only one component, which is phi, the flux. And this flux cuts these coils and makes this E1 and E2. So the same flux makes E1 and E2. So for this reason, E1 and E2 will be in same phase. And the angle or the phasor relation between E1 and E2 and phi will be something like this. E, we know E is equal to minus negative of d phi by dt, and let's say phi is equal to phi m sine omega t. So if we put this phi value in this E equation, then after derivation, the equation should be something like this: cos omega t. Okay, then minus take a negative, and phi m sine pi by 2 minus omega t, and let's take out this negative sign. Then we have n phi m sine omega t minus pi by 2. So in these two equations, this one between this one and this one, we can say that this induced voltage E is lags this phi by 90 degree. Okay, so we have to draw any of these induced voltage with the relation by the lagging of 90 degree with this phi, with this flux. So now what should we write first, or what should we do first, E1 or E2? So at the very first time we should do the secondary side circuit. Let's remove this part because this won't come in my work further. I think if I write this thing in black color, then it will be easy for understand. So it was the phi, it was Im magnetizing component, and now I have to draw induced voltage E1 or E2. But first of all we will take the secondary side because this will be convenient for us. So if I draw E2 like this, then this will be correct because E2 is lagging this phi by 90 degree angle. And then if we look at the secondary side, we can see that this is inductive circuit somehow. You know, we have the leakage reactance, we have the coil, and this circuit will be something like inductive. So this I2 will lag this E2 by some angle, like this one. I2 is lagging E2 by some angle. Then we have to draw these voltage components. First of all, take these resistive components. These resistive components will be in phase with this I2. So I have to draw I2 R2 like this. Then these reactive components will be leading this I2 by 90 degree. So I have to draw like this. I2 X2. This I2 X2 leading this I2 by 90 degree angle. May my angles not be perfect, but you know, you have to understand in such a way. Then rest of the thing will be V2. Yeah, this is V2. So this I2R2, I2X2 and V2 make this V2. So we have completed these equations. But for the simplicity or for better understand, let's take this V2 vector here like this. Then we can say that there is an angle between V2 and I2, which is theta 2, let's say. So what is this theta 2? This theta 2 is actually the power factor angle at the secondary side of the circuit. So the real power at the secondary side will be P2 is equal to V2 I2 cos theta 2. So we have done with the secondary side of the circuit, and let's go to the primary side. So we have already done the magnetization component of the primary side. We have done with that. Then we have relation with Im of Iw, which is the core loss component, and Iw will lead this Im by 90 degree, because in a parallel circuit, if we have resistive and reactive components, if a current enters this circuit, and it will be divided into two parts, let's say I2 and I1 and I2. This I1 will lag this I2 by 90 degree because of this reactive elements. So I have to draw Iw with the lag of 90 degree with this Im. So I am drawing Iw like this. Then we know that I0 is equal to Iw plus Im. So if we add vectorically IW and IM, we can get I naught. Let's reduce IW a little bit. Okay, then what we have? We have this I2 prime component, and what we can see in this circuit, I2 prime is the negative of I2. So if I just flip this I2 by 180 degree angle, then I can get the I2 prime. I am not taking the actual magnitude of these components, just for the understand. So now if I add I2 prime with I0, I can get I1. Okay, taking the KCL rule in this point, so I can get I1 very much easily. And then it's time to write these components, but first of all we have to take this E1. E1 will be in phase with E2. I have already told that, because these two things are made for the same flux. But I don't need E1, I need the negative E1. Then the negative E1 should be something like this. Okay, then I have written this one. I have to get this component, so this component will be in phase with the I1. So this should be something like this: I1 R1. Then I have to do this one, and these components will just lead this I1 by 90 degree angle. So it is doing so. This I1 X1 leading this I1 component by 90 degree. And then if I add this negative E1 and this resistive component and also the reactive components, then I will have V1 like this. Then if I draw an angle between V1 and E1, let's say call theta 1, then it will be the it will be what? It will be the power factor angle at the primary side. So the primary side power will be P1 is equal to V1 I1 cos theta 1. So we have got the power in the primary side. Actually these are the real powers, the power in the primary side and also in the secondary side, and I have got all the phasor diagram of this transformer. This transformer is a real transformer, and such a real transformer has these types of equations, and this is the vector diagram of this transformer. So I have drawn this phasor diagram in my freehand with the mouse, and it was a little bit difficult for me, and I think this diagram is not so perfect. So I request you, first of all, try to understand all of the things, and if you have any questions, then do it in comment section, and practice this vector diagram in your own note with pencil, with pen, and also with the scale to make it perfect. So this is it for now. Thank you, and see you in the next video. Bye bye.